Hi, I'm Robert, and in this project I predicted combined cycle power plant output from physical conditions using Microsoft Excel and the CRISP-DM methodology. I compared a simple linear regression model using only ambient temperature to a multivariable regression model using all four features and selecting by validation error comparison. I'll present my decisions, reasoning, and results in the next few minutes. Our objective is to create a model that predicts the plant's net hourly electrical output in megawatts using the ambient conditions available or provided. I'm looking at this through the stakeholder lens of operators and planners. They care about a couple things. First, the forecast is accurate enough to plan confidently, and second, that the model is clear enough to trust and explain. As such, I'll clearly be looking at parametric algorithms. Our business goal is simple: more reliable energy forecasts to support scheduling and resource decisions. In OKR terms, the objective is better forecast reliability, and the key results are lower root mean square error and fewer last-minute redispatches. There are important trade-offs to consider. If the goal is pure forecasting accuracy, we might favor more complex models like tree ensembles. Or if the goal includes control and operational levers we can pull, interpretability matters more. So a linear model, or a clear explanation layer on top of a complex model at the very least, can be the better choice. In this project, I start with linear models to keep things transparent while still improving accuracy. For success criteria, I'm using three metrics. The primary metric is root mean squared error, reported in megawatts, because it tells us the average size of our error directly in the business units, which is easier for our stakeholders to understand. I did also track mean average error for robustness to outliers and R squared to show how much of variation in output the model explains. The data set has approximately 9,500 hourly rows or observations. Possible features to include are atmospheric temperature, exhaust vacuum, ambient pressure, and relative humidity. The target we're predicting is hourly power output in units of megawatts. Based on an intuitive understanding of the data via scatterplot, I hypothesize a strong correlation between temperature and energy output. After reviewing the data, I determined no further data cleaning was required because there were no missing or invalid values in the dataset. Upon first glance, there are no obvious significant outliers present, but that is something that I might want to check again if time allows. I used a 60-20-20 split, training on 60% of the data to fit, validating on 20% of the data to choose the model, and then testing for the final one-time check on the remaining 20% of our data set. I used frozen random number generation splits to prevent data leakage and used Microsoft Excel's data analysis toolpack's regression tool for both the simple and multivariable models. Holdout validation here is a practical choice because the data set is large and I'm using Excel rather than a more coding intensive program. I did also attempt the project using Google Vertex AI AutoML, where I would have considered a more robust five-fold cross validation, as that would have been appropriate since our task is condition-based and not time sequence dependent, but ultimately rejected this approach given my limited coding ability. Here's a view of the data set and some of the scatter plots. I compared two models again. First, a simple linear regression using only temperature, where power was equal to the intercept plus the slope times temperature. Second, a multivariable model with all four features included. I didn't use lasso regression here because we only have four features. Excel doesn't include penalized regression in its analysis, and the validation set should already guard against overfitting. Here is the results of the analysis that I'll review in a minute. Here are the models based on the training set and their formulary. So for the results, on the validation set, root mean squared error drops from 5.34 megawatts with the simple model to 4.47 with the multivariate model. That's a 16% reduction. On the held out test set, that improvement continues and holds with a 19% advantage. Additionally, mean average error also improved. That tells us that everyday errors got smaller, not just the occasional big misses that drive root mean squared error. In other words, the model is more consistent and easier to trust for the planning, which is helpful for our stakeholders. Note that R squared also increases from around 0.9 to 0.94 because the multivariable model won on validation set and generalizes on the test set, and therefore I selected it as the final model. Connecting back our model metrics to business impact, recall that the outcome we want is steadier schedules and lower costs. The outputs we measured are validation and test set root mean squared error with mean average error and R squared as supporting signals to show that our model explains the variance in target values. My working hypothesis is that a lower root mean squared error should reduce redispatches and lower operational costs. So that's what we would monitor going forward to track performance as new data readings are provided. As mentioned kind of earlier, if time and budget and funding continue to be available, iterating on the model using lasso regression to improve feature selection would be a reasonable next step. And following that with more complex tree-based models and more five-fold or k-fold cross-validation for potentially capturing nonlinear effects. Thank you all for listening and evaluating my presentation.